Assalamu alaikum, everyone. Good evening. I hope you are all doing well. We're meeting again in another talk of School of AI, and today we're hosting Mr. Amir Almamma, who is an M1 MIAJ student at State University at Rennes 1 and AI and data science engineer. The talk he's going to be delivering for today is going to be about differentially private machine learning. And I hope you will enjoy the talk. If you have any questions, make sure to drop them as usual. We'll do our best to answer them all. And yeah, that's all. Thank you so much, Amir, for accepting our invitation. And the stage is yours. Thank you.
Thank you, Aya. Thank you, School of AI, for the invitation to host this talk. So let me share my slides. So hello, everyone. I am Amir Almamma, artificial intelligence and data science engineer, and Master 1 student at ESTEC at l'Université de Rennes, France. And today, I'm going to deliver a talk about differentially private machine learning. Today's mission is to try to learn together what is differential privacy and what does it have to do with machine learning. Because I think that most of the audience of School of AI already know what is machine learning and what are learning algorithms, but few of us are concerned with the privacy aspects of these learning algorithms. So in this talk, we will try to break down our understanding of differentially private machine learning into several questions. At first, we will try to understand what is a privacy and how and when do we need it. We'll try to give a formal definition of privacy, and then we will understand what is differential privacy. Differential privacy is the general is the most commonly used form of privacy or formal way of defining privacy, and it's used in machine learning. So next we'll understand actually the topic, which is differentially private machine learning models, and we will try to based on our understanding of the intuition of behind differential privacy, how does it apply to the case of machine learning models. Then we will take a step further into the literature, and we will try to study the deep learning with differential privacy. We'll see how this theory that we got introduced to applies to deep learning models training. So at first, intuitively, machine learning, as we know, has as a goal is extracting information from data. So the goal of machine learning is to take data, try to model it, and try to get information from it. While privacy, on the other hand, pulls in the opposite direction, which is protecting the private data from leakage. So how can we combine the two? How can we combine the two approaches of dealing with data in order to make a machine learning model that actually learns the model of the data and extracts the useful information while keeping the private information, the sensitive information, private. We will see how differential privacy enables us to build models that train well, that perform well, while keeping some privacy guarantee. At first, let's try to understand what is privacy. In the context of data privacy, we get concerned by the privacy when we are trying to move data from a trusted environment or from a high trust environment into a low trust environment. So So basically, like for example, a healthcare institution has the healthcare data of users, and these users and this data has private fields of the users, and also some data that is useful to understand a community's health situation. So a healthcare institution can have as a motivation to publish a version of the data for an educational purpose, to educate the community about the healthcare situation. So this this publishing technique, if not done properly, can leak um, can leak uh, can leak can leak data that is private. So how can we ensure that the version that we are publishing of the data is not it does not leak sensitive information, but keeps the useful information available to the public. Okay, so moving forward, a lot of there like humans invested big effort in trying to define private data publishing techniques, or secure data publishing techniques. And one of the earliest, or one of the oldest standards of publishing private or secure ways of publishing data is anonymization, where we take the data and we remove the private fields, like the name, obviously the first name, and the email address, or like the phone number, or any private fields of the data. But this is not enough. This step is necessary, but it's not enough before publishing the data, because it can be vulnerable to background attacks. Background attacks are attacks that an attacker do when he has some background knowledge about the user. So even if he doesn't know the private identifiers of the users, he can still connect the publicly available data to trace it back to the private identifiers of an individual user. So anonymizing an individual user's data and publishing it is not enough. So some researchers developed other techniques of grouping individual users' data into groups that share the same pseudo identifiers. So we replace their identifiers with the pseudo identifiers shared between multiple individuals, making them into groups before publishing. So the first, like most intuitive way of doing it is k-anonymity. K-anonymity publishes a version of the data where individuals are in groups of at least k individuals per group. While this ensures that if that an attacker cannot distinguish individuals inside the group, cannot distinguish k individuals inside the group, it still has low privacy guarantees, because it doesn't have a constraint on the diversity of the target information in this group. So even if we make sure that a certain group has 100 or maybe 50 users, 50 individuals in it, but still maybe the target data is not diverse enough inside this group. So even if we don't know exactly the private exact identifiers of the user. Only from the pseudo identifiers we can guess the target data, like the symptoms that this user has in the case of healthcare data. Here comes the definition of L diversity. L diversity um, L diversity publishes to publish a version of data that respects L diversity means that we publish a version where groups have at least L diverse or L different um, target target data or sensitive data, like the symptoms. This way, we make sure that in one group we have enough diversity that even if an attacker identifies that an individual exists in that group, he cannot identify with confidence it's his symptoms or anything about his private data. Even though this is an improvement over the K anonymity, this is still not enough because multiple versions can be published of the data. So if the healthcare institution publishes a version this month and then publishes another version 3 months later, and a certain curious attacker has the two versions of this data, then he can compare them, and when he compares them, he can know he can make conclusions on the data on the individuals that we introduced between these two publications, even if they are grouped. Here comes the importance of differential privacy. Differential privacy. If we say that our way of publishing data is differentially private, means that what we publish about the data is not sensitive to an individual contribution in the data. So it's not sensitive to adding or removing one individual in the dataset. So the formal definition of differential privacy, we say that mechanism F, which is mechanism F. A mechanism is any function. In this scenario, a mechanism is any function that takes data as input and outputs a random variable. So you can imagine a mechanism F as a count query on the data. The count query takes data as input and outputs the count number. So in this case, the count query is considered as a mechanism. So we say that F is considered private if its result is not sensitive to small changes in data. That means if adding one row to a dataset leaves a big trace on the result of the query F, then the query F holds low privacy guarantees. That means that if an attacker comes at an instance and queries the dataset before adding this individual, and then querying it after adding this one individual, and he can notice a significant difference, then the traceability, then he can trace this individual. He can know that we added this individual. One individual contribution should not have an effect on the function or on the mechanism, but rather the mechanism should give us information about the global dataset or the whole dataset, and while masking the individual elements of this dataset. So what this formula basically says, that it says that, well, if we have a dataset D, and another data set, a neighbor data set D prime, with a distance of 1 between them. Distance of 1 means that D prime is one more individual or one less individual than D. So we say that the probability that the answer of the query F or the answer of the mechanism F is equal, the probability of the answer of the mechanism F on D prime equals to S. And this is the probability that the answer to the query F on D equals to S. So what this formula says is that the probability that the answer is S is less or equal than the probability of D prime, that the answer to F on D prime is equal to, is the same answer with a certain exponential of epsilon and with a certain delta. So if we can prove that our mechanism guarantees this property, then we can say that our mechanism is delta epsilon differentially private. And this is very important. So how do we do that? And one of the most famous ways, or one of the most used ways of ensuring differential privacy, is by adding noise to the answer. So we can add Gaussian noise, or Gaussian. We can sample the noise from a Gaussian distribution, or other distributions. So yeah, this is basic. Like, for example, in the case of the count query, we instead of returning the real answer to the count query, we return an answer plus a certain noise. And this way, the attacker will not know if the difference in the answer came from an individual contribution or from the noise. So after that, we got some understanding of what is differential privacy. Let's go to machine learning and then come back to the relationship between differential privacy and machine learning. So machine learning is a family of algorithms that learn, or that learns to perform a certain task. And there are many classifications of machine learning algorithms. We can classify them by supervised, unsupervised, and reinforcement learning algorithms, or we can classify them simply by the task they are doing. So the classification, regression, clustering, or dimensionality reduction. So in the context of differential privacy, we know that the process of training a model takes data and outputs a model. And if we formalize it, if we formalize this process of training with this way of formalizing the process of the training, we can consider the training mechanism as we can consider the training as a mechanism. And to say that a machine learning method is differentially private means that this mechanism need to have a privacy guarantee. What that means is that the model that we select out from the training process, or the model that the resulting model of the training process, is not sensitive to a one individual's contribution in the data. And this is the basic definition of a differentially private machine learning model. If you can ensure that previous property of differential privacy, by taking in consideration that F is the training mechanism, then we can say that this machine learning algorithm is differentially private. So typically we want the released model to be differentially private, but we still want it to perform with a certain closeness to a true model. So we want it to be private and hide individual information, but we still want it to perform as good as, or closely good to a true model. Here comes some questions that different researchers answered in a different way, depending on the use case. So firstly, how do we define like the distance between two models? Is the distance between two models defined by the difference between their parameters, or do we define it by the output of the model? So and again, what do we consider a true model? We can consider a true model as the result of a training process without noise. And also we can consider a true model the actual model of the data. So if you have like the actual distribution of the data, or the actual model of the real data, and not a learned model. So here this is like the definition of the way what do we decide in our case a true model is, and the distance is affects the way we try to prove the differential privacy of the machine learning algorithm, depending on the case. So now how can we like create the most important question is that how can we create the release model? So how can we go from maybe a true model to a released model? One simple idea is to take the true model, to train machine learning algorithms until fully trained, and then add noise to the final model's parameters to get the release model. Another idea is to while training the true model, we add noise to the target. So this is a different idea. We can add noise to the target or to the objective, and we call this an objective noise. So in many other there are other ideas probably in other research works, but they depend on the level of privacy that we want from our use case, and they also depend on the use case itself, or the possibility the model we are training itself. So now an interesting paper was published in 2016, deep learning with differential privacy, which had as a main idea of ensuring privacy by adding noise to the gradient of the stochastic gradient descent algorithm during training. So we said that we can create a model to be released by adding noise to the final model, but in this case, in this paper, the author suggested that we add noise along the training to the gradient of the gradient of the SGD. So let's try to discover that a little bit deeper. So here, this is the outline of differentially private SGD algorithm. What the basic modification that the authors did to the SGD is is adding noise to the gradient before doing the descent step. And the argument was that, like I said, adding noise to the final parameters of the model may lead to destroying utility of the learned model by adding noise based on the worst case analysis. So if we fully train the model and then we try to add noise, then we may add it based on the worst case in order to that may lead us to add a very large noise, because we try to cover for the worst case scenario. So instead, they decided to add noise to the SGD all along to the gradient all along the training. And also, also an important thing is that we should keep track of the privacy loss during training and limit the total privacy budget. So we have a certain privacy budget, and the more we train, the more we add noise, the more we are using the data, and each step of adding noise has a certain cost to the privacy, and we should limit. We should have a certain privacy budget that the model cannot exceed during its training. At the end, we will have a model we'll publish a model, and then we will know which values of delta and epsilon of the differential privacy that this model holds. So which level of privacy guarantee that this model have. So in the experiment, like in the paper, they did experiments on the MNIST dataset, where they trained the deep learning model with different levels of noise, and they observed the training accuracy. They observed the accuracy during training, and observed also the evolution of how they consumed the privacy budget during the training. So the experiments showed that the model converged even with noise. That's a good sign, achieving more than 90% of accuracy before consuming its privacy budget. And the paper also demonstrated that the final model to be released has a privacy budget of 2.55 and 10 to the power of minus 5, the differential privacy. The paper also had another contribution of the way that it estimates the privacy budget. So there were works before that like even if we train the model in the same way, we cannot say with confidence that it has a low privacy budget. But in this paper, they introduce another method of calculating the budget that proves that the model has a very strong or very tight privacy guarantee. That was the main idea of the paper. And if you are interested with language models, and you want to learn more about how the content of this talk, how we can apply to language models, I invite you to do a further reading to differentially private fine-tuning of language models paper. I can add the link to the description of the video, or you can look it up. And in this paper, we will try to learn more about how we can apply all these principles to the NLP or to the NLP case. So a summary to sum up what we learned in this presentation. We learned that K anonymity and L diversity replaces sensitive information with pseudo identifiers but are vulnerable to background attacks. We also learned that differential privacy adds noise to hide sensitive information and provides a formal definition of privacy. And this differential privacy is important in the case of differentially private machine learning. Differentially private machine learning methods rely on this definition of privacy to publish models with privacy guarantees. And in the paper Deep Learning with Differential Privacy, authors added Gaussian noise to the SGD gradient. With this modification, stochastic gradient descent becomes a differentially private stochastic gradient descent. So this was the summary of what we covered during this presentation. I hope you learned, and thank you for your time and attention. And if you have any question, I will be more than happy to answer them. Thank you. So
Okay, sorry, I thought the mic was on. Anyways,
okay.
I guess we're gonna be answering some questions right now. So the first question says, what is the relationship between federated learning and differential private machine learning?
So actually, I didn't. Well, this is an interesting question. I didn't cover it up during this talk.
Okay.
Well, actually, I can like look it up again, look it up more after this talk and discuss it, because this is a specific area of machine learning, and it maybe has a different way of dealing with differential privacy during its training. So it may be different than deep learning, but yeah, it must have its own constraints that I didn't discover during my learning journey. What was the second
another
question?
question. Are differentially private machine learning algorithms commonly used today?
Well, yes, they are used basically on they are used in cases where privacy of the information is important. So they are used in the cases of, like I explained, the healthcare use case, or any other use case where the privacy of the initial data is important. So that's where
Okay,
we
thank
find
you.
it. We don't find it commonly, but this is where we find the answer. Differential privacy.
Okay, fair enough. Another question. What are the possible attacks that can be yelled against differential private machine learning?
The possible attacks against differentially private machine learning. Well, basically, we can say that each like model that we publish that is differentially private has a certain limit of has a certain limit of the privacy guarantee. So we can say not all differentially private models are the same. So some are better than the others, and depending on how well did we do how well did we add the noise during the training, we can publish a very private model or a low privacy model. So basically, but the biggest problem with that comes with machine learning, with differentially private machine learning models, is not exactly the vulnerability of them, but that we sacrifice a bit of the performance of the model. So we sacrifice a little bit of the accuracy of the model compared to a model that is trained on without considering the differential privacy. That's the downside of it. It's not actually the attacks on it. Yeah.
I guess there's a trade-off between the accuracy of our model and how well we want to secure it. So it's trade-off.
Yes, this is a trade-off to. It depends on how well. It depends on how well we want our model to be secure, and how much can we sacrifice of its performance.
Okay, and this will depend on the field, of course.
Yes, of course.
I guess there are no more questions. I think so. So anyways, I would like to thank you so much for the talk. It was really interesting and I enjoyed it so much. I hope everyone else has enjoyed it too. Thank you again for the talk. School of AI community will be so grateful, hopefully. That's all. Thanks everyone for your kind attention.
Yeah, thank you so much for the invitation, and thank you for your time and attention during this presentation. And I wish you good luck in what's coming next.
Thank you. Thank you so much.